CE Chapter 8, Reaction Rates and Equilibrium. We're at the review point. I put on a picture of our lab, so hopefully you remember what they were. On the left-hand side there, remember you've got the reaction with the sodium sulfite and the sulfuric acid to give the sodium or sulfur dioxide. And then we had the reaction with hydrochloric acid and magnesium on the right, and the antacid and the water on the right also. And then down at the bottom, a reminder of our equilibrium lab and what your graphs look like. They all come together in what we're going to be doing for the review. Okay, so we have exergonic. Remember, that is with heat out. And endergonic is where I'm putting heat in. When I talk about exergonic or endergonic, think exothermic and endothermic. That might help you because we've talked about those terms before. When I look at an activation curve with these, exothermic, you're going to have an activation curve where the reactants are higher than the products. Remember, these are your reactants and these are your products. For endothermic, you're actually going to have your products end up higher than your reactants were. Okay? Now, you'll still need to be able to label all parts of the activation curve and be able to understand that. So let's look at one real quickly. I'm just going to grab a couple here. This one is what? Exo or endothermic? It is exothermic. So if we look at this and we've draw our little dotted gram here, this would be my reactants, and you've drawn enough of these now that hopefully you know what is going on here, and this would be the products. This is your change in energy. This is your activation energy down to where your reactants were, so E of A. And this from your products to the top of the curve is E of A prime. Now, I can also from this, I always want to start with my reactants at 0. I can see that my products are going to have a negative delta E. This is exothermic. I could read off the graph and draw my own thing here. Now remember, when I have a catalyst is going to come in and actually just lower the activation rate. The reactant and the products still stay where they are, but a catalyst, which is a matchmaker, which lowers the activation energy, will actually take and lower that activation energy and the amount of energy it takes to get going. Forgot the L. Okay, so let's look at another one. We can do the same thing for endothermic, where it's ergonic, where we end up above. So we still have our reactants over here. It's still easier to start at 0, and my products over here. And again, I do my little dotted line for my reactants and my products. This area right here is delta E. The area from the reactants to the top of the curve is E of A, which is the activation energy. And distance from products to the top of the curve is known as E of A prime, which is activation energy of the reverse reaction. Okay, so we've done a ton of these, so hopefully this is not anything new. Now, think about it this way. If I have an exergonic thing, what's going to happen to entropy? Now remember, entropy is the amount of disorder. So as I heat things up or put heat into it, like an energonic or endothermic reaction, what's happening to my entropy? Well, my entropy is increasing because I'm putting more energy into it. What about, you can also think about this as, here's solid. If I put energy into it, then I get liquid. Put energy into it, now I've got steam. So I'm increasing in entropy, or the amount of disorder. Think about this other way. Over here, entropy is actually decreasing. And the reason why is just the opposite. I'm going from a higher energy to a lower, whether it be the water or back to a solid. So hopefully that will help you. Solid, of course, has the lowest entropy, the lowest disorder. Liquid has the next less disorder, and gases have the highest disorder. Okay, so here's my artistic design. Boy meets girl, and we get a couple. So that's just the same as saying A plus B yields AB, right? Well, the problem is it's not as easy as that. I can't just put A and B in the same area and expect them to react. They have to have enough energy to react. So if a boy sits on one end of the classroom and the girl sits on the other end of the classroom, there's never going to be a reaction. There has to be some energy involved. They have to get up and get moving. So what kind of conditions are necessary for a chemical reaction to occur? Well, they've got to be in motion. Okay, so they've got to be in motion. What else? Well, they've got to be opposite charge. So they've got to be a boy and a girl. Okay? They want to be able to react. They want to be opposite charge or different charges. And they want to be in the right orientation. And what I have to help people with this is that, you know, if a boy and girl are walking away from each other, that's not the right orientation to start a reaction. They've got to be walking towards each other, and they've got to be facing each other in order to have a reaction. If one sidesteps, then it's not going to happen. Now, along with this, we need to talk about the reaction rate. When we talk about reaction rate, we talk about how fast this reaction is going. Remember, that is the change in concentration versus the change in time. Okay, so if I had a classroom full of kids, and I just let them mingle around for a while, eventually some of them would pair off. Now some of them won't, so they'll stay single. So I've got this reaction going. And the change in the concentration of couples, or let me put that again, change in the concentration of my reactants, or my single girls and my single boys, over the time that I allow them to stay without me supervising, gives me the reaction rate. Okay, so we're going to do a couple of those. Before I go on anymore, we need to talk about molecular collisions. The faster the motion, the faster the reaction, the better chance they'll bump into each other. They must bump into each other for a reaction to occur. They've got to be going fast or got to be moving. They've got to have the faster the motion, the more probability that they'll hit each other in the right direction, and the relationship between molecular collisions and reaction rate is direct. A reaction is also spontaneous if conditions are present for that reaction to progress or go forward, and the reaction does. So if I have a spark, that's my activation energy, and then the reaction will head forward on its own. Okay, but boy and girl have to collide, or A and B have to collide in order for a reaction to take place. They can't just go by each other. They've actually got to engage. Now, sometimes with these reactions, we have what is known as a catalyst. And these catalysts are like the matchmakers. They get them together. They're exactly opposite of inhibitors, which keep them apart. So inhibitors would be putting them in two different rooms. A catalyst would be somebody coming and getting one out of one room and taking them to the other room. Okay? I can only lower the activation curve, the amount of energy it takes, if I have a catalyst. So I have to use a catalyst to lower the activation energy if I want it lowered. Whether it be a homogeneous, which means the same phase, or heterogeneous catalyst, which means different phase, it still works the same. Okay, so we have factors that influence our reaction rates. We actually did at lab, remember? But there are 5 of them: temperature, particle size, presence of a catalyst, concentration, and nature of reactants. We did the lab with the temperature, particle size, and concentration. We didn't put a catalyst in there, but a catalyst, remember, just lowers the activation energy. The nature of the reactants. I like to think of it like a classroom, like I was telling you about. Depending on the presence of a catalyst and matchmaker, or the nature of reactants. If I put all guys in the same room, they're not going to pair off normally. Okay, so factors that influence the reaction. If I have a system at equilibrium, what is true? In the equilibrium lab, we found what when we did the lab with the straws and the thing. If I'm at equilibrium, what is true is that the rate forward is equal to the rate backwards. Okay, so that meant the water that I moved from each of those containers when I was at equilibrium was the same. So it's equal to the reverse rate. A reaction at equilibrium, remember we can do our KEQ, reaction at equilibrium is equal to the concentration of the products to their exponents divided by the concentration of the reactants to their exponents. And the only thing that can affect KEQ, is temperature. So temperature will affect it. If I have an exothermic reaction, where's heat? It is on the product side, right? If I have an exothermic reaction and heat is on my product side, then if I want to decrease KEQ, then I want to lower the amount of products I have. So I want to increase the temperature, and that will lower KEQ. If I want to increase KEQ, then I want to lower the temperature because that will make more products, forcing it forward, and my KEQ will go up. Now if we think about it for an endothermic, now I could call these endogonic or the exergonic or endogonic. Now think about it this way. Endothermic means I'm putting heat in on the reactant side. So if I want KEQ to go down, then this time I want to put the temperature down, because when I put the temperature down, then it's going to force more reactants. If I want the KEQ to go up, then I'm going to increase the temperature. Okay, so generally when we talk about KEQ, the more, if it's bigger than 1, the more products we have. If it's a huge number, then we know the reaction will go mostly to completion. If KEQ is at 1, we're at equilibrium. We've got about the same amount of products as reactants. If KEQ is less than 1, then we know that the reaction doesn't proceed forward very much. In fact, it mostly stays as reactants. All right, so remember as you're writing your KEQ. Okay, we've got these little things here. We go to and we would just write KEQ, concentration if it's in concentration, C to the X power, D to the Y power, divided by concentration of A to the A power, concentration of B to the B power. Okay, you need to be able to write the KEQ and then plug in the numbers they give you for C, D, A, and B, okay? The last thing that we need to talk about is Le Chatelier's principle, and I know a lot of you are struggling with that. It's going to be on the test. It's going to be on there strong, so make sure you know. I'm going to do a general equation. So A plus B yields C plus D, and I'm going to add heat on this side. So this would be exergonic or exothermic in the reaction. Now, if I add B, Remember I told you it will shift away from where I add, so it'll shift this way. So that means this will be less, this will be more, and this will be more, and this will be more. Okay, but I'm shifting forward. Okay, now if I look at something else, do this off real quick. Whoops, too far. It didn't want to do that. Okay, we'll just put another one up there. So here's A plus B, C plus D plus heat. Okay, now assume this time I only have one gas, and this is the gas. If I increase the pressure, it's going to go to the side, so I'm going to increase pressure, and that doesn't matter how I do it, but if I increase pressure, since this has 1 and this has 0, then the reaction is going to go forward because it goes to the side with the least amount. If I decrease the pressure, then it's going to go backwards because it'll go to the side that has the most gas, and it's just gases. All right? Now, what happens if I take and do that again? Want to just worry about temperature. Okay? If I have the temperature increase here, that means I'm putting things in here. I'm adding heat here. Since I'm adding, it's going to go to the opposite side of where I add. So this is going to go reverse. When it reverses, then my D is going to go down, my C is going to go down, and my B and A are going to go up in concentration. Okay? Now, remember that heat, when I'm dealing with heat, is the only time that it will affect the K. So my KEQ here, if you remember from a couple slides before, is going to do what? Well, if I add heat, I'm making less product, so it's going to go be smaller. Okay? So what happens if I decrease the temperature? If I decrease the temperature, that means I'm making a hole here. That means it's going to shift to fill the hole. So I'm going forward. And my KEQ, since my products are going to get bigger, is going to be bigger. Now, temperature is the only thing that will change KEQ. KEQ has to stay the same otherwise. So you need to be able to say, okay, looking at any one of them, they won't ask you the whole thing here. They'll pick and say, okay, what happens to B if I do this? All right? So let's just erase this again real quick. And let's do just a concentration one. Okay, so if I do a concentration, say that I said I want to add C. And this time I'm just going to pick one that I want you to tell me what happens to it. What's going to happen to D? Well, if I add C, then I've got to shift away from C, so it's going to shift this way. So it's going to go reverse. That means I'm going to decrease D because I'm going to use some of D to combine with C to make A and B. Okay? If you're still having problems with this, you need to come in and see me because it is on the test, and it's on the test a lot. Okay? If I had a KEQ, now that was 0.00025. What does that tell me about this reaction? Well, it tells me I have mostly what? Reactants. Say that instead I had a KEQ of 3.5 times 10 to the 76. Well, that means it almost goes to completion going forward because it's such a huge number. I have very little reactants. Remember that an inhibitor just slows down a reaction. So if I have an inhibitor, it just slows it down. It doesn't stop it. It makes it very slow. Okay, that's it. Good luck. Again, if you have any problems, come and see me. Actually, let me just do one more thing. Remember on our equilibrium charts, some of you got something like this. Some of you actually just went like this. Some of you had something like this. Okay, where do I know when it's at equilibrium? Well, I know it's at equilibrium when we got those 4 trials the same, remember? So the 4 trials the same are going to be out here. Not in here where they're equal amounts going forward and back, or what was in the cylinder, but it's when we had the 4 the same at the very end, right here. The 4 the same. That's when I was at equilibrium. Okay?